Chapter 8. Okay, so what am I doing here? I am going through the chapter summaries for an introductory calculus-based college physics course. I am actually going by the book Halliday, Resnik, and Walker, 9th edition. And so I've gotten all my other videos gone through chapters, and the playlist for all those will be down below, and we're on chapter 8. And so, I don't completely... This is not the way I would do everything. This is not the exact format I would use, but it's what's common. So that's why I'm going through it. Okay, let's just get started. Because chapter 8 is about potential energy and conservation of energy, and it really builds on chapter 7. Chapter 7, this is the stuff from chapter 7, so I put it up here. This is all chapter 7 stuff. And if you haven't watched that video and you're jumping into this one, you might have a little bit of trouble. So these are some of the big things that we have from chapter 7. Number 1 is this definition of kinetic energy. The first is the idea of energy. It's a different way of looking at a system. Instead of thinking about force and changes in velocity and acceleration and Newton's second law and time, we can think about it with this other idea we call energy. And so the first kind of energy that we define is kinetic energy. And this says that if an object is moving, then it has kinetic energy. That depends on the mass and the velocity of the object. Now, velocity is a vector. So really, this should be 1/2 m, the velocity vector magnitude squared, because you can't square a vector. Okay. The other big thing was the definition of work. If I have some force applied on an object, I can calculate the work, which is essentially like the energy you add or take away from a system. And work can be negative. And we can calculate it with a variable force as an integral. So you have to integrate the force along the path. You got to know the path for this. Okay, now, it can get pretty difficult. But in your course, an introductory physics course, it's probably going to be fairly straightforward. They're not going to give any weird paths. This is going to be mostly straight. And if the force and the path don't change directions, then you can write this as, or magnitude, you can write this as the following dot product. So the work is this F dot delta R, where delta R is the displacement and F is the force. And then just a reminder for dot products, because we are going to use these. The dot product, you just take the x components, multiply them together, so it's be fx delta x, plus the y components added together, plus the z components added together, and that would be the work. And then over here we have the definition of the work energy theorem. This just says the work is a changed energy, which we're going to change that a little bit, and let's get started on that right now. So the first is this idea of conservative force. Now we're doing chapter 8 stuff. Conservative. It's hard to spell when you're making a video. I don't know why, but it is. So imagine that I have some point A right here, and I choose, and this is the essentially the picture that most books use. I go to point B along this path like that. And there's some force acting on this, which it could be variable, it doesn't really matter. It's just some F. So at any particular point, dr is that way and F is that way, and it can change. And so I calculate the work as the integral from point A to B, and I need the actual x, y, and z coordinates of that, of F dot dr. Now, suppose that I do this integral from A to B, but I choose a different path. I go this way. And again, let's call this work 1. Let's call this work 2. It looks the same here because we write it the same, but this could depend on the path of the particle. This camera looks a little tilted. Oh, I see what the problem. My little Lego mount. Okay, that's not really better. I'll fix it later. So if work 1 equals work 2, and that's not actually it. It has to be all passive. It doesn't matter what path you take, but the work is just some product of some function of, I don't want to write it that way. But if the work does not depend on the path, we call that a conservative force. And if the work does not depend on the path, then you can take the easiest path, right? Also, if the work does not depend on path, then, and if work 1 is equal to work 2, then work going from A back to A, a closed loop would be 0, right? Because the work would be work 1 right here, and now I'm going in the opposite direction, so it'd be negative work 2, but they're the same, and so they would add up to 0. And so that is a conservative force. So the path is, the work done is independent of the path, and the round trip would be 0. Now there's some mathematical definitions for this that could do it in a little bit better way, but you won't do that. Okay, so now let's think about work. So remember that work is the change in kinetic energy. That's all we saw so far. But imagine that I want to move this to the other side. So I have 0 equals negative work plus delta K. Now, if this does not depend on the path, I can actually write this as negative work is the change in potential energy. So I'm going to move the work to the other side of the equation and call it a potential energy. And so since we know the definition of work, we know the definition of the change in potential. It's going to be negative the integral from point A to point B of F dot dr. And this is what we call potential energy. So it only works for conservative forces. And it also is important to think about the system here. And I talked about the system in the last chapter. And this book, I don't think, does a super great job of it. But imagine that I have some collection of objects. This is my system. If the interacting objects are both in the system, then it's possible to make it a potential energy. Okay, so let's look. But if they're not, you can't make it a potential energy. You can't have potential energy for one object, right? Because you'd have to have both the interacting objects in the system, and forces are always an interaction between two things. Okay, I think it's time to I don't normally do a lot of examples, but I want to do the following. I want to show that the gravitational force on the surface of the Earth, I call it Fg, is going to be equal to mg, where g is the vector 0 x hat plus negative 9.8 newtons per kilogram y hat, and I'll just do it in 2 dimensions. I want to show that that's conservative. Okay. I want to imply that it's conservative by calculating the work along 2 different paths. So let's go this way. Let's go from A to B along these 2 paths. So let's first calculate work 1. So let's call this y equals 0, and let's call this x equals 0. So that's my origin. And let's call this a distance h and a distance s. So to calculate work 1, I have a straight path, and my force doesn't change. So I can use the simple definition of F dot delta R1 plus F dot delta R2, because I actually have 2 pieces. So delta R1 is going to be this vector going from here to there. So we can do that by inspection. It's going to be 0 x hat minus h y hat, right? Because we're going down in the negative. You could do final minus initial. You could do the point 0, 0 minus point 0 h, and you could get that too. And then delta R2 is going to be equal to s x hat plus 0 y hat, goes in the s direction. And then I have my force up here, so we just need to do these dot products. So let's say work 1 is going to be this force dot that, so I get 0 times 0, which is 0. And this is called this minus g. Minus g times minus h, so I get plus gh. Now I got to do this one, and so I get 0. Oh, that's m. I forgot the m. The m's in there too. 0 times S is 0, and then mg times 0 is 0. So let's get the work done along this path is mgh. Okay, now what about that path? Let me get a new piece of paper because I don't want to be crunched in here. Let's just move that up a little bit. Okay, I'm going to cover that up. So now I need this delta R. So this delta R is going to be, you could do it in a couple different ways, but if I know this is the point 0h and this is the point S0, then delta R is going to be equal to the change in x. So it's going to be S minus 0 x hat plus the change in y, which is going to be 0 minus h y hat. So this is going to be equal to S x hat plus negative h y hat. And then my force is 0 x hat minus mg y hat. So let's take the dot product. F dot delta R. And that's going to be equal to 0 times S plus negative h times negative mg, so plus mgh. And you'll notice that this is work 2, and that's also equal to work 1. So in this particular case, the path does not matter. So that doesn't mean necessarily that it's a conservative force, but if that was not true, it would definitely not be a conservative force. Okay, so since it's a conservative force, I can say the change in gravitational potential energy is going to be equal to negative the work, but the work is mgh. So it's going to be mgh, because it's negative of that. In this particular case. In general, I can say delta U is mg delta y. And that's the potential energy, the gravitational potential energy near the surface of the Earth. That's a change in. The change, delta, the change is super important here, okay? Because we don't really deal with, the work energy principle deals with work, which is an integral from point 1 to point 2, so you really always have a change. Often you will see this, U as a function of y is mgy, and that's fine. But the problem is that it depends on where you put your y is equal to 0. Okay, so this is very useful. Just don't think it's real, right? Because two people could disagree on what what the value of mgy is, but they wouldn't disagree on delta U, the change in potential. Okay, so now it is important to realize that in order to do this, in order to have this, I have to have my system. Let's say I have a dropping ball. My system would have to have the ball plus the Earth. I have to have at least those two objects in there in order to have a gravitational potential energy. You can't have the potential energy as just a ball. Okay, it has to have at least two objects. So I have to include the Earth in my system. And that's why I think it's important to go ahead and declare what is your system, right? Because once you declare your system, you can say what the potential energy is. Now, here's the other important thing. Now my work energy principle looks like this. Work is delta U, I'll call it UG, plus delta K. So in this case, if I have that as my system, I'm going to have a change in gravitational potential energy and a change in kinetic energy. I could have some work on the system. I could have a rocket or someone pushing on the ball or something like that. But I could not do work done by gravity and a change in gravitational potential energy. Be very careful not to do that, okay? Okay, so the other force that we looked at was the spring force. In one dimension, they said Fx is negative K x, assuming that, I don't really like writing it that way, but that's fine. If the further you stretch the spring, x, the greater the force, and k is the spring constant, tells you how stiff the spring is. And so we did the work done by a spring. We said that work is going to be equal to the integral of negative kx dx, and from point, let's say from x equals 0 to x equals s, and we got negative 1/2 k s squared, where that's the stretch. Okay, so but now you see, if and I'm not going to show you this, but it does turn out that it doesn't matter what path you take. So if I have a spring like this, and I go here from 1 to 2, and then I also go from here, it turns out that the integral doesn't depend on the path. It only depends on the endpoints. So that means that we can make a potential energy from this force. And so if you have a spring in your system, then you can have a change in and spring potential energy of 1/2 K S2 minus 1/2 K S1 squared. And in general, we say the potential energy as a function of S, the stretch or compression, is 1/2 K S squared. Okay, let's talk about the conservation of energy. The book defines this thing called mechanical energy, and I'm not a really fan of that, but that's fine. Mechanical. So before we had work is the change in kinetic energy. Now we're going to say work is a change in mechanical energy, where mechanical energy, E mechanical, is kinetic energy plus potential, whatever potentials you have. Now assume that I have a system with objects and there's no external forces. So in that case, work is 0. So I have I'm just going to call it the change in energy is 0. So if it goes from position 1 to position 2, this is going to be E2 minus E1. And so if that's equal to 0, I can say E2 is equal E1. This is the conservation of energy. It says that if there's no work done in the system, the total energy doesn't change. Okay, and that's fine. And then you could write this as K1 plus U1 equals K2 plus U2. Now, that's fine. I think it's much better to always go back to just work is the change in energy. And sometimes that work is 0. Okay, a lot of people use this, a lot of people jump to this, but the problem is that you can get yourself into some trouble depending on how you set this up. So I always like to start with that, but you do you. Okay, I want to talk about something that comes up. Oh, let me do this real quick and then I'll show you. So here we have delta U as the integral of from point 1 to point 2 of F dot dr. That's our definition of the change in potential. So what if I take the derivative of both sides? And this is a little weird, but I'm going to do it anyway. So if I do that, I get, let's do this in one dimension. In one dimension, I have, so it's only moving in the x direction. I have delta U is negative 1 to 2 fx dx. Now I'm going to take the derivative of both sides. So this is going to be du is negative fx dx. Now I can solve for fx. I get fx is negative du dx. It's kind of a big deal. And then you could do the same thing for y. Fy is negative du dy. And then fz is negative du dz. So this says that if you know the function of the potential, you can find the force that made it, instead of what we've done before, which is know the force and find the potential. So you can go backwards. Sometimes you want to do that. Okay, so now one of the things that they talk about, and it's kind of useful, are these potential energy curves. I don't normally do this, but I'm going to just look at the book here. Okay, let's look at this book and let's interpret these potential energy graphs. So here's just some function, some potential energy function as a function of x. There's a one-dimensional potential, the potential energy, and it has some change in position. So there's not a time, it's position. So that's what we have. Now, the first thing we could do is think about the force, right? So if I want to look at the force as a function of x for the same thing, all I'd have to do is take the inverse derivative of that. So you notice right here, it has a negative slope. So this would mean that during this slope, the force would be positive. And that's why over here it looks positive. Down here, this is a really important point. You'll notice that the potential is 0. The potential is 0. And the force is 0. Why is the force 0? Because the slope right here is 0. Over here, the force is also 0 because the slope is 0. Okay, so be careful. Don't think, oh, the potential is 0, the force is 0. That doesn't have to be true. Right here, the force is 0. And that's how you get this curve right here. Now, one of the things that we like to do is imagine you put an object in a system here. And we can represent an object with no work on the system. Then the total energy has to be constant. So we can draw that as a horizontal line. And if this object is moving this way, once it gets right there, the total energy has to be the potential energy. And over here, you can't be, right? Because the only way to be right here is to have a negative. The kinetic energy would have to be negative. And because U plus K is equal to energy. And you can't have negative kinetic energy because it's a velocity squared. And there's no way that can be negative unless it's imaginary. Or you have a negative mass, which we don't have. Okay. So the kinetic energy in any of these systems is the difference between the energy and the potential energy graph. And so you can imagine this object moving along here at a constant kinetic energy because the distance between these is constant. And then it's going to increase as it goes this way because the distance between these increases. It goes. You can think of it going downhill, and then it goes back uphill, and then it goes downhill, and so forth. So one of the other things that you want to look at is oscillations, because right here we call this an equilibrium point. It's an equilibrium point because if I move this way, the force pushes it back that way. If I move this way, the force pushes it back that way. So that's an equilibrium position. This is that's a stable equilibrium position. This is an equilibrium position because the force is 0, but if you push it a little bit, it's going to roll away. Okay. Let's see. There is something about internal energy. Let me just say this real quick. There was an example, and it's a great example. Imagine the following case. An ice skater, and she pushes away from the wall. Okay. So if she does that, she's going to increase in kinetic energy. But there's no work done on her, right? There's no work done because the force on her doesn't move. F dot delta R is 0 because the force doesn't move. She moves. So one way we can account for this is say the work is 0, and that's going to be the change in kinetic, which is positive, plus some change in internal energy. So we can do that. Now, we could also treat this as a point part. There's two things. There's a real system and a point particle system. In the real system, we actually use the distance the force moves to calculate the work. In the point, and we have other types of energies. In the point particle system, we treat this as just a point particle. And in that case, the work done is the distance the point moves, but there's no potential energy. Okay, so using these two together, you can usually solve a bunch of stuff that you don't normally do. And I agree, it can get really complicated. Okay, just be very careful about declaring what your system is. Is it real or is it point particle? You really need to practice this. Again, like I've said in all this stuff, this is just a short overview. I'm not telling you everything you need to know. I'm not doing every single problem. You still have to work these physics problems. You can do it. I mean, look at all the other people before you. Look at the physics professor for your class. That person took introductory physics. That person did not get 100% on everything. That person had to work. You can be that person. It just takes time. Okay, so keep at it, and I'll post the next chapter soon. Let me know if you have any questions.